Good evening. So today is the last class before quiz 2. And yesterday we just discussed about the anti-bunching, that is kind of um, correlation function you can expect, which cannot be explained classically. If you just consider both light as a quantum photons, comprised of photons, quantum photons, and detection is also happening in a quantum fashion, then I think normally whatever classically correlation function is anticipated, it's not possible to obtain in some situations. So there may be possibilities that the photon-wise anti-bunched photon stream can be demonstrated, and people started working on it. And in 1977, I think this is Kimble, Dagenais, and Mandel. These three scientists, they reported first the anti-bunched photon stream. That is in 1977, means about 40 years ago, 45 years ago. So how they did, you see, this is some kind of sodium vapor beam is, I think, passed through a transparent tube, and such that the flow rate would be such that at a particular, atomic flow is very weak. So at a time, perhaps one atom can be visualized with an objective, microscopic objective. So from this side, you have a excitation laser will be there. So when excitation laser is there, and at a particular point of time, so it may be multiple sodium atoms will be excited, but the information, that fluorescence, that means photoluminescence, that can be collected by the microscopic objective from maximum from 1 at a time. And then you collect this one, use a special pinhole to remove some noise, background noise, special filtering, and then you use a HBT experiment to check how whether they are anti-bunched or they are getting bunched. Particularly, you want to measure this correlator is there, start stop time. So you just one photomultiplier, if hit one photon and detects it, then you start counting. When this signal coming here, then your timer starts, and wait for the next signal coming from this here. That is the general concept of the HBT experiment. So you try to see that, okay, number of counts you are getting depending on time interval, you just plot a histogram and check. And then you see this type of behavior is there. Okay, so that means time delay, when time delay is 0, that means you are not really getting any coincidence. That means at one single point, tau equal to 0 means you are detecting here as well as here. So 0 time gap you are not really getting. So as you keep on whatever histogram you analyze, then you see that this gap is slowly increasing, exceeding 2, and then it is at far end when tau is much longer. If you see some occurrence is happening for tau longer time. So those things if you put, then you can get, say, it is stabilized to 1, you can normalize this one. So this is how it is happening when laser beams are coming. So a sodium ion, actually it takes very short time for excitation, but once it is excited to come down to ground state, it takes longer time. So that emission time is somewhat longer. Even if you just illuminate with a CW laser, then what happens at a time, CW means continuous wave laser. So at a time, one atom will be excited, but it takes at least hour time, little longer time to emit. Okay, so that means your emission rate will be distributed. It will have certain gap for photon emission. Okay, so that is how you get a almost regular interval anti-bunched. It will not, there is no chance of the bunching, because at a time one sodium atom it will be emitting only one photon, and then you have to wait for the next excitation and coming down. So that way you get anti-bunched. So that was the first report. If you want, you can just download this paper, and it is simply written. If you read, you can understand also. This is just for demonstration purpose, that experimentally people demonstrated what is anticipated quantum mechanically. Okay. Now thing is that that is once you get that one, that means you can actually determine when is the photon coming, and you can select them, and that can be considered as a single photon. So then it is actually 2000, so about 20 years ago. So a lot of experiment went on. This is actually sodium atoms, and afterwards people tried to demonstrate this anti-bunched photons in solid state. Solid state meaning kind of some kind of color centers. People used also diamond crystals where vacancy will be there, nitrogen vacancy, and then try to excite, so that if it is in solid state, that means you can go for application, device application purpose. So one interesting results is that this is in the semiconductor, because anything you demonstrate in semiconductor, I think technologically it is viable. You can go for mass production, and you can really go for system level application also. So this was the first time in 2000, Missler et al. That was published in Science. It's a very famous journal, and they have demonstrated a micro disk, something like that. This type of disk structure, even in our lab here in CNNP, we can fabricate this type of structure, 5 micrometer dimensions also, but quality maybe you can do that. But for this particular material used, we don't handle. It is actually different way it is actually grown. It's a algase material, 3-5 semiconductor based. So this structure consists of a micro disk of 5 micrometer, and then 0.5 micrometer post. This is the post. There is a bottom, there is a post, you see, that is also algase. And the disk area consists of 100 nanometer of gallium arsenide. That means this disk, top disk, that means 100 nanometer thickness gallium arsenide is there, and then indium arsenide quantum dot layer is there. One quantum dot will be grown like this. Here schematically it is shown. This is a gallium arsenide, algas. Sorry, this is actually your algas and gas, and then here you have gallium arsenide top and bottom, 100 nanometer top, 100 nanometer bottom, and then in between you have a indium arsenide quantum dot, and that dimension is about 45 nanometer and height about 3 nanometer. So you can grow that type of technique you can demonstrate. And if you just do some photoluminescence, then you can get that emission will be around 950 nanometer. Okay, so photoluminescence, if you do, the emitting wavelength will be 950 nanometer. So this quantum dots, I think it's a well known for emitting single photon. It was demonstrated that it was actually that time without knowing the how it is happening, because that time people thought that okay, there will be certain kind of quantum states will be there, because it is a quantum dot. So conduction band, valence band, there will be separation will be there, and it was known that in a quantum dot there will be some kind of exciton formation will be there. So I think in solid state physics, if you know exciton, if you have heard, anyone heard about exciton in the class? I think anyone, if you have taken solid state physics course, particularly in physics, or maybe solid state device course you have taken, perhaps you have heard about excitons. No one? What about, I can ask someone maybe, yeah. Physics, I think I see some physics PhD students also. Anjana?
Sir, I have heard about Exciton, but I don't remember exactly.
Yeah. So I think exciton is the what it is. You know, normally electron and hole, if they come closer, what happens normally, if it is electron in the conduction band and hole in the valence band, normally electron will be recombined to the valence band and energy will be released. Okay, but in certain situation, for a pure crystal, and what happens uh, when you are injecting electron hole in a diode, particularly you are in a certain region, the electron hole, they won't recombine. Rather, what they do, they are coupled like a atom, you know, like a hole, you know, that means positive charge. It looks like equivalent to a positive charge, and electrons like a, okay, it's an electron. So in hydrogen, for example, if you know that there will be one positive charge hydrogen atoms, and then surrounding it electrons will be, one electron will be moving. That is what hydrogen atom is there. So in a crystal, semiconducting crystals where electron holes both are there, so certain situation can occur where uh, electron, instead of recombination, they will be coupled in such a way that it will be combined like a atom. Just a hole will be there surrounding that, one electron will be, if you just model like a Bohr theory, that's some Bohr radius you can calculate, and it will be just coupled like that. So there some kind of Coulombic interaction will be there, you know, that's existence of a atom, how it is hydrogen atom. If you consider, there will be some kind of quantum mechanical processes there because of the Coulombian interaction. Coulombian force will be there, as well as your centripetal force will be there, and that balances. So that way you can explain. That's a atomic structure, how it is there. So that electron hole, when they are coupled like that, that electron will have certain kind of small energy, binding energy will be there. Like electrons, when it is bound to hydrogen atom, it has some binding energy will be there, so that that electron can be removed from the hydrogen atom, right? So here also some kind of energy, binding energy is there, so that way it is coupled, but it will not collapse. It will be like a atom, it will be there. That is actually called exciton. So when electron hole pair, they will be coupled together, and they will coexist, but they will not merge together, they will not recombine. Then together it is like a one atom, and that one atom, it can transport, or it can be transported also. It can be transported. When it transports, you know, it is like a carrier. Normally carrier transport means you have a charge it will be carrying, right? But here, because electron hole combined is neutral, so no charge is being carried. But since they are separated, anytime if they recombine, it can release energy. So that means to form exciton, you need some kind of certain kind of work to be done, and that work can be released when that exciton ceases to exist. That means that will be electron will be released, and then once it is that binding energy released, there will be some recombination, and then photon will be emitted. So that type of thing is called exciton. So in a quantum dot, whenever you are just injecting, I will be just explaining a little while later, when you somehow inject electron and hole, then they will be creating like a exciton, and that exciton will have a lifetime. So that lifetime, if you just create exciton and inject into the quantum well, right? So they are actually, depending on the lifetime, it will be de-excited and some photon will be generated. So that lifetime actually controls that kind of anti-burst type of photon emission. So here it is same way like sodium atoms in the previous things. So here in this semiconductor it is demonstrated, and then you could actually see the HBT experiment if you see, and the correlation function if you see, if you just see the delay, that exactly at 0 you see the minimum correlation, minimum hitting. Okay, so that means actually anti-bunch. That means it says that once you in your HBT experiment here, uh, here once you get a signal, at the same time you don't get a signal for the other one, so there will be minimum. So it shows that it is minimum. So if you get this type of characteristics, that means you can say that they are basically singled out. Photons are singled out, they are anti-bunched. Okay, so that was done. Of course, that type of exciton, this binding energy they can get, it's a very small binding energy. It's in the order of room temperature energy that is sufficient to supply that type of energy. That's why this operation has to be done at very low temperature. So here, for example, it is done around 4 Kelvin, very low temperature, so that thermal energy will not supply to remove that binding energy, so that this exciton will not be existing, so you won't be getting. So that quantum dot, because of the exciton emission, you can actually get your single photon emission, and that was demonstrated first time in solid, particularly semiconductor, so that people are a little bit excited to go for that. And then you see,
Sir,
yes.
sir, could you explain what is the importance of that microdisc structure? We can make condom otherwise also, right? So why did they specifically go for that microdisc?
That's a good question. So what is happening whenever you are using a laser? This laser actually is creating electron hole pair here in the gallium arsenide itself. Okay, and then this electron hole pair, when it is tunneled into the quantum well, in the quantum well, you know that band gap variation will be there. Normally in indium arsenide, the quantum band gap is lower. So electron will be trapped in conduction band and hole will be trapped in a valence band inside the quantum well. But while trapping, they will be somehow coupled like an atom. Okay, so that is why if you use this disc-like structure, that means your laser light comes here, whatever it is electron hole pair will be generating, it will be directly can be tunneled into the quantum well. It can be trapped inside the quantum well. Okay, if it is something else, just quantum well, if you are using, and directly you cannot, where from you will get electron hole pair? To inside the quantum, if it is electron hole pair is being generated inside the quantum well, that will recombine like a normal photoluminescence. But what happens, electron hole pair generated and they form, as it tunnel inside, they transport inside, they are forming like a exciton injection, exciton injection. That is how it was demonstrated that time. Okay, is that clear?
Yes, sir. Sir, then this gallium arsenide base itself, we can use indium arsenide, right?
You can use.
Any material as the base, I
Yeah,
mean
yeah, yeah. I
gallium.
think any quantum dot, it should be actually somehow electron hole pair should be generated and that exciton should be there. Here, intention is that you need a direct band gap semiconductor. Normally, exciton formation normally happens. Otherwise, if it is indirect band gap semiconductor, there also happens, but you need phonon interactions. So it is like a laser diode. You know, laser diode, you need a direct band gap semiconductor. To electron hole pair to recombine to get photon emission. Silicon, for example, is not a good laser diode. So here also you need direct band gap semiconductor. That's the whole idea.
Okay,
Okay.
sir.
And then here one drawback is that you have to have your laser for photon emission. But normally for circuit, for device performance, it's always good to have your, if you can create exciton by means of driving electrical current instead of laser pumping. It is some normally first ruby laser was demonstrated, pump was light, and then people tried to demonstrate solid state laser. So, but again light was used as a pump. Ultimately diode, when it was discovered, that time people could find that okay, from electrical current you can actually generate photons. So here also intention it would be that if you can make uh, electrically driven single photon source, and that was after a couple of years, and this Yuan et al. They demonstrated, that was also published in Science journal. That scheme is shown here. You see, this is a just any substrate you can use as a gallium arsenide. That's a 3,5 semiconductor things. And here also you can use your indium arsenide quantum dot, and that quantum dot you can grow. And depending on the growth ambience, okay, you can actually somehow in a regular or irregular manner, you can just create few grow few quantum dots. Okay, so that is actually different type of MOCVD process already developed, and you can actually create this indium arsenide quantum dot layer. And if you see that this is gallium arsenide, similar fashion, this is gallium arsenide, but what things it is done, you have an insulator and then you can have a contact material here. This is actually your p-type doping. This is actually p-type doping, and this is will be sorry, this is p-type doping, and this is n-type doping. This is n-ohmic contact. N-type doping will be there. One side will be n-type doping and bottom side will be p-type doping. So this side is p-type and this top side is n-type. And in between, intrinsic region, that means if you are forming a diode, there will be a depletion layer, as if your quantum dots are lying in the depletion layer. Okay, and then you have p-type ohmic contact and n-type ohmic contact, and then you can actually bias. You can give a forward bias, so that you can from the p side you can inject hole, and this side you can inject electron. Okay, and since there are many quantum dots will be grown, you can actually, after grown, you can find out that what is the regularity, what is the periodicity of the quantum dots are there. Depending on that, you can create some kind of aperture here through which any photon will be emitted that can be collected. So that is called emission aperture. So top view optical microscope, if you see that N side, N contact it is shown here, and P contact it is, you see it is cross section it is shown. From the top view you can say that. So this is the N basically you are getting contact from the top, and P you are getting from the bottom. So accordingly you are making just this type of structure. It's called mesa structure. So in this mesa structure you can get a good electron hole confinement. That's why it is used. It's a well-known structure for semiconductor technology, and particularly 3,5 semiconductor technology. So that is used. And if you see that AFM, I think a very good resolution atomic force microscopy, you could show that quantum dot positions after growing this white spots. You see these are actually quantum dots, some kind of luminescence you can see that. And then they did some kind of, using this, they did some kind of correlation measurement by forward bias. Forward bias means they are giving after bias they give some pulse voltage source. So you see 80 megahertz repetition rate, and you keep this device, enter device, for 5 Kelvin low temperature, so that your excitons are not really collapsed. And so 80 megahertz means you could expect every 12.5 nanosecond one pulse is there. So 80 megahertz means time duration will be 12.5 nanosecond. 1 over 80 megahertz, you can find out that 12.5 nanosecond. Okay, so in the absence of a peak at 0 time interval indicates that low probability. You see this is the number counts using your HBT. They have used a special type of detector that's called single photon avalanche detector. Both side, and correlator is there, timer, start. And then you see that so correlation, if you are just trying to see at zero coincidence, you are not getting any pulse here. So as you go per time both side, if you are just counting time, so you will see the pulse regularly coming. Single photon count is coming every 12.5 nanosecond. So that is that at zero, it is like a correlation measurement, right? So number of events, you are counting number of events, and so at zero actually you are not getting zero time delay, you are not getting. So that is actually says that it is single photon emission is happening. Okay. So the problem is that here also the main experimental difficulties that have to be overcome before these single photon sources find more widespread application is the low overall quantum efficiency and the operating temperature, which is again we have electrically driven, but again problem is that this low temperature process still, I think this single photon or whatever quantum photonics devices, quantum computer people are developing, they are all basically low temperature story. So that is one problem here also. For a single photon source you need low temperature. So they again here the first two results on quantum dot single photon sources are described by Mishler in 2000, and Santori in the physics review letter. They have seen all of these are used optical trigger pulses. This is the first time electrically driven, and these two they were demonstrated, one for I think single photon source with normal gallium arsenide, another is this NV center in diamond crystal. So this NV center, whenever diamond crystal you are creating, that is actually different technique. That is a different technique, not like Exciton things. So they are just color center, one quantum things will be there. But in semiconductor, it is a excitonic emission will be there. So if you are interested, also these references are given also, particularly those who are doing research and what is the state of our technology, if you want to know. This is a very current topic. You will see that. And the next I'll be just showing a couple of slides that although people demonstrated this single photon sources because of the exciton, all this theory, everything developed because of the bulk theory, bulk semiconductor theory, but till I think recently also people do not know what is the actual dynamics is happening when you are actually getting a single photon source from a quantum dot. So here is another one method. It's a very interesting one. I just it's a interesting in physics point of view, because you know normally the photon is your both wave nature and particle nature is there. These guys, this Weiler et al. In 2004, they published a paper in physics review. So where they simultaneously showed that the photon emitting, they are actually showing both wave nature as well as particle nature. Okay. So what they did, they also developed same quantum dot, similar type of quantum dot, but in indium phosphide quantum dots. Again, 3-5 semiconductor, but instead of indium arsenide, indium phosphide, and gallium indium phosphide embedded. This instead of gallium arsenide, gallium indium phosphide. So depending on their facility, everything they try to demonstrate this one, and this is the setup they have used. You know, this is the, but here actually they have not used electrically driven. They have used a laser source and then excited, and then whatever single photon is coming here, then you use this. There is a flippable mirror is there, and beam splitter you are using, so that you can actually filter and pump laser, whatever the pump laser you can also stop. There is a band pass filter somewhere will be there. Where is band pass filter? I don't see here. This is the F. F is the band pass filter, I think. Yeah. So I think BF I have written. That should be BF, I think. Band pass filter will be there, so that you can actually stop this laser excitation when photon comes. Then you have a Michelson interferometer. So Michelson interferometer, normally, you know, it's classically you can see the interference fringe. So that is what they observed. Okay. And also simultaneously they could image using Fourier spectroscopy method where is the location of the, if you just image the location of the quantum dots, because it is, there would be not only one quantum dots, multiple quantum dots will be there, but you can find out location of the quantum dots, and then you can follow only one quantum dot. You can consider, you can take image frame by frame, and then you can see what is happening, intensity, how it is changing as a function of path length of the Michelson interferometer. Michelson interferometer, you know, we have discussed earlier. So they have used both the arms, they have used one for CCD, another for our detection here directly. Whatever it is coming here from the CCD, and something it is coming here, and for this here you are using 2 APD. Whenever you are just getting a photon simultaneously here, or you can also access here depending on the flippable mirror. These mirrors you can actually block, you can flip there, stop to going Michelson interferometer, you can just directly hit to the HBT. Okay, so here also this flippable mirror, you can just remove that one. Instead of sending to spectrometer, you can send this one. These are flippable mirror, and these are normal HBT. And here you could see actually the what do you call that, excitonic emission. And the two types of excitonic emission is there. One is X, another is X2. You know that why two types of emission they could observe. You know, I said that exciton means it is like a hydrogen atom. Hole and surrounding it electron will be loosely bounded with some kind of binding energy. And you know, in a hydrogen, two hydrogen atom again combine together to create a hydrogen molecule. So similarly here, two excitons can be coupled together also, and then energy will be splitted, and then you can see two different type of energy emissions you will be seeing. So you can select one of them, and you can try to see classically what is the visibility it is dropping, like whatever the HBT experiment classically you are getting, and then also you measure the HBT experiment there you can see, and something also you are getting visibility you are getting, and here you are getting that at 0 there is a minimum, and then outside time is changed, then you can get you can ensure that it is a single photon emission is happening. All right. So this is till now it was demonstrated, and people were trying to use them for different type of applications. But actual physics, what is happening, how exciton is forming, what is the time dynamics, etc., that was not known till today. And just a recent paper I find that Deng et al. They published recently in Nature Communication, just May 2020. So you see, that's a exciton generation processes in quantum dots for single photon emission. I think actual title is, I think, something deciphering the exciton generation. Deciphering exciton generation in quantum dot. That means it was not known till today how these excitons are getting generated, what is the time dynamics, etc. And they did, these guys, they did very sophisticated experimental setup. You see, there is a quantum dot will be there, and a voltage source will be there, and here some exciton will be formed. And you see, this is your device, and then this is actually called electron transport layer, and this is hole transport layer. So you are just supplying from the outside through gallium arsenide or whatever things are there. You are just supplying electron and hole to the quantum dot, and then at the same time you use a pulsed laser also to excite the electron hole pairs and exciton. Normally two types of exciton will be created. One type of exciton will be because of the photons, and another exciton you can create because of this injecting electron and hole pair here, okay, from the outside bias. So from that point, analyzing this thing, you can read this 5-6 pages and little bit of theoretical things. I am still trying to understand that, but what I got the interesting message is that what happens, how it happens, with data they prove that first what happens, electron normally, hole injecting to the quantum well is very a little bit tough. It's relatively, because it is heavier, it goes slower. So what happens, once it is electron, it moves inside, okay, and in the conduction band of the quantum dot, it traps, it get trapped. So once it is trapped, then it will help to bring, because of the Coulombian force, it will help to attract hole into the quantum dot also. And hole when comes, that hole will reside in the valence band, and then that time it actually coupled together, electron hole pair. So what is in the process, what happens, that first a neutral quantum dot, it is negatively charged by the electron, and then a hole comes and then it becomes again neutral, but that time it is exciton is formed. And this exciton, once it is formed, what happens, the electron, once it is in the conduction band, then the quantum dot is small, depending on the size, it will not allow further additional electron to come in there, okay, because of the Coulombic repulsion forces, something will be there. So that means only one exciton will be generated. At a time, only one exciton is generated, even though you are giving a DC bias continuously. And this exciton, it will actually, once it is formed, it will actually, after certain time, it has a lifetime. It's about 17 nanosecond lifetime they have reported. So within 79 nanosecond, there will be actually releasing a photon. And then entire process, this electron going and then pulling hydrogen. So this entire process, it takes several microseconds. You see that it takes a microsecond, and then once it goes, it can emit like that, emission. So in this way, first there will be a negatively charged. They have analyzed also if it is possible that positively charged is first hole is moving and then it is positively charged and electron is moving, and in this way they could actually demonstrate that what is the actual procedure basically. So you can find out now from this work actually helps to model that what would be the rate you can generate a single photon, and for application purpose it will be useful. So that is one way people are trying that with quantum dot. And I think you can find, if you search also, a lot of latest research going on to have a single photon source in nitrogen vacancy in diamond crystal. I think only few people in the world working on that. I think reproducible results are not coming, and the device is not yet ready for application in circuit level. So this thing will continue to improve, but we have some other ways of getting into single photon source. For example, in photonic integrated circuit like silicon, that we'll be discussing in future classes. And before that also we need to discuss a bit about the other ways of, because you know that there are another method is subpositional light, and another is we've discussed what is this actually, anti-bunched one. So we need to find if other ways are there. This is what anti-bunched photons could be generated, and you can get single photon, etc. What are the other means, useful means are there, and people are using, also people are going ahead for circuit applications. That will be moving into the next class. Okay, so till this point we will have the quiz 2. I'll be sending all the slides, maybe starting from the beginning. Up to 150 slides, 52 slides I'll be sending, and based on that your exam will be there. I stop here. If you have any questions, just a couple of minutes I can spare. Any question?
So am I audible?
You are audible.
Yeah, so is the quiz pattern similar to the first
Similar to quiz
several
one.
assignments?
Similar to,
There are some topics which don't have any mathematical derivation or formula as such. So, like, is there any chance of descriptive questions or
yeah,
something? Or
there
is it
yeah, everything.
problem solving quiz?
So you see, whatever we discussed, lot of things are. It's a, it is courses. Why I am discussing a little bit of technology. You know, the course name is Quantum Photonic Devices and Technology. Yeah.
Yeah.
So some technology hurdles we want to discuss, because a lot of, once we go for theory, there are rigorous theories are there, quantum information processing theory, and there plenty of subjects are there, also courses are there. But this is something we are discussing, that what is close to the application, what is close to the practical device fabrication, etc. So descriptive questions, it may come. For example, Exciton related question I can ask. Why not? You should read.
Yeah, yeah, sure.
Yeah.
Thank you.
So the for example, operating Exciton related and maybe closely related things like interference, quantum interference. Particularly when we talk about quantum interference, that means this G2 correlation measurement, and classical interference means Michelson interferometer, all those type of things. So those related mathematics, whatever is there, that will be asked. And I think this book, I think last couple few lectures, I just followed this book. I've taken some information from here and there. I think this book you have now, all of you are having, right? Can you see this book?
Yes, sir.
Yeah. So this book, I think what I discussed, I think up till chapter 6, chapters up to chapter 6, and part of chapter 7 also we discussed photon number state before quiz 1. But I think mostly photon number state, or this is no, chapter 6, up to chapter 6 we discussed. We'll be just discussing now coherent states and squeezed states. So up to chapter 6, and I see that there are a lot of questions also there in chapter 6. Okay, so those questions you can try to solve also, and also you can whatever assignment given, similar type of questions will be given, and I may pick a couple of questions which is relevant from these papers, also references I have given, that type of things. You try to read. Yeah, I think if you follow my lectures, whatever discussed, I think questions will be based on that only. Yeah, like quiz one also, you most of you got very comfortable. Similar type of questions will be there. Yeah. Fine. Any other question? If not, then I
First
stop.
midterm question portion is not included, right?
Which one?
First midterm
Which one?
of, yeah.
No, the questions will be on the whatever we discussed from quiz one. So I think last time we have given slides up to 76, right? You remember all the slides? Now I think I just today I realized that today 152. So up to quiz one it was 76 slides, and another 76 slides we have discussed up to quiz two. Okay, last 76 slides will be covered. And yeah, I think we are about 2/3. So I expect that I have to take another at least 16 more lectures needed. So that means 4 weeks, complete 4 weeks we need to complete this course. All right. Any question? So we can stop here maybe.